When most people face a difficult problem, they begin by looking for an example. How did another company solve it? What does the industry normally do? Which method has worked before? This is reasonable. Human progress depends on imitation. We learn language by copying. Engineers reuse proven designs. Doctors follow procedures built from accumulated evidence. A world in which everyone reinvented everything from the beginning would be slow, expensive, and dangerous. Elon Musk often begins somewhere else. Instead of asking how a problem is normally solved, he asks what the problem is made of. Which parts are physical facts? Which parts are assumptions? Which requirements come from nature and which exist only because someone once wrote them into a document? This method is usually described as reasoning from first principles. It is often presented as the secret behind Tesla and SpaceX, as though saying the phrase automatically produces electric cars and reusable rockets. It does not. First principles thinking is not magic. It does not replace knowledge, experiments, skilled teams, capital, or years of difficult work. It can also produce terrible decisions when the supposed principles are incomplete or wrong. But when used carefully, it changes the starting point of a problem, and that can change everything that follows. To understand the difference, imagine that you want to build a bridge. Reasoning by analogy begins with existing bridges. You study their materials, shapes, costs, construction schedules, and safety standards. Then you modify what already works. Reasoning from first principles begins by asking what the bridge must physically accomplish. It must carry a certain load across a certain distance. Gravity will pull downward. Wind and temperature will create stress. Materials have measurable strengths, weights, and prices. People must build and maintain the structure safely. Once those facts are clear, existing bridges become useful evidence rather than unquestionable rules. Perhaps the standard design is already best. Perhaps it contains unnecessary weight. Perhaps it was shaped by an old manufacturing limitation that no longer exists. The goal is not to reject tradition because tradition is old. The goal is to understand why the tradition exists. Musk has explained first principles thinking with the example of batteries. The conventional statement was that battery packs were expensive and would remain expensive because batteries had always cost a great deal. That is reasoning from history. The first principles approach asks what a battery contains. It contains materials such as metals, carbon, separators, electrolytes, casings, and other components. Those materials have market prices. If the raw ingredients cost far less than the finished battery, then the high price is not a law of nature. It comes from processing, manufacturing, yield, scale, supply chains, design, and profit margins. That does not mean making a cheap, safe, durable battery is easy. It means the problem has changed. Instead of asking why batteries are expensive, the team can ask which transformations make them expensive and which transformations can be redesigned. The same reasoning shaped SpaceX. Rockets were extraordinarily expensive. The normal conclusion was that spaceflight was simply an expensive activity. Musk asked what rockets were physically made of and compared the approximate value of those materials with the price of the finished vehicle and launch. The difference was enormous. Again, this did not prove that a cheap rocket could be produced immediately. A rocket is not merely a pile of aluminum, copper, titanium, electronics, and fuel. It must survive extreme vibration, pressure, heat, aerodynamic forces, and complex guidance demands. It must be manufactured with exceptional precision and tested carefully because small failures can destroy the entire vehicle. But the material comparison revealed that expense was not determined only by the atoms. Much of the cost came from how rockets were designed, built, certified, operated, and discarded. The word discarded became especially important. Imagine taking a commercial airplane from New York to London and throwing it away after landing. Even if the fuel were inexpensive, air travel would become unaffordable for almost everyone. Traditional orbital rockets often lost major hardware after a single use. If a booster could return, land, and fly again with limited refurbishment, the economics might change. The problem was not simply how to make a rocket cheaper, it was how to stop destroying the rocket. That reframing gave SpaceX a different engineering target: rapid and reliable reusability. Many organizations improve within the existing definition of a product. They make a disposable rocket slightly cheaper or a gasoline car slightly more efficient. Musk often challenges the definition itself. What if the rocket lands? What if the car is designed around a battery rather than converted from a gasoline platform? What if the factory is treated as a product that can be redesigned? What if the number of parts is not fixed? What if the accepted schedule reflects bureaucracy rather than physics? These questions can sound obvious after someone asks them. Before that moment, they may feel unreasonable. This is one reason breakthrough ideas often appear simple in retrospect. Once the new frame is visible, the old frame looks strangely narrow. But asking an unusual question is only the beginning. Musk has described a 5-step engineering process, sometimes called the algorithm. The sequence matters. First, question every requirement. Second, delete every part or process that can be deleted. Third, simplify and optimize what remains. Fourth, accelerate the cycle time. Fifth, automate. Most organizations instinctively use the reverse order. They begin by automating an existing process. Then they try to make the automation faster. Then they optimize individual steps. Only much later does someone ask whether the process should exist at all. This creates an absurd but common result, an expensive machine performing an unnecessary task with extraordinary efficiency. The first step is therefore to question the requirements. A requirement is anything the design is supposed to satisfy. The component must have this shape. The report must include these fields. The meeting must involve these departments. The material must tolerate this temperature. The approval must pass through this person. Requirements sound authoritative. They often arrive in spreadsheets, technical specifications, contracts, regulations, or official procedures. Because they are written down, people treat them as facts. But requirements are created by humans. Some protect safety. Some reflect customer needs. Some are legal obligations. Some exist because a senior person once made a guess. Some were correct 5 years ago but have never been updated. Some are compromises between departments. Some are included because no one wants to accept responsibility for removing them. Musk's version of the method insists that every requirement should be connected to a person, not merely to a department. A named person can explain the reasoning and update the requirement when evidence changes. A department cannot be questioned in the same way. It becomes an abstract authority. This does not mean ignoring experts. It means refusing to transform expert judgment into permanent law. Imagine an engineer saying that a support bracket must weigh 2 kilograms because the structures department requires it. The first principle's response is not, the structures department is stupid. It is, which engineer calculated the load? What assumptions were used? What safety margin is necessary? Has the surrounding design changed? The requirement may survive. It may even become stricter. The purpose of questioning is accuracy, not automatic reduction. This distinction matters because careless first principles thinking can become arrogance. A person with incomplete knowledge may dismiss a rule they do not understand and discover too late that the rule protected against a rare but catastrophic failure. A useful question is not, why are experts stopping me? It is, what evidence would make this requirement necessary? Once the requirements have been examined, the next step is deletion. Delete the component. Delete the process. Delete the meeting. Delete the inspection. Delete the handoff. Delete the feature. Then see what breaks. This is more radical than ordinary efficiency work. Efficiency asks how to perform a task with fewer resources. Deletion asks whether the task deserves resources at all. In engineering, every part creates hidden costs beyond its purchase price. It must be designed. It must be documented. It must be sourced. It must be shipped. It must be stored. It must be assembled. It can fail. It can be installed incorrectly. It may require tools, inspections, repairs, software, or training. One component can create dozens of secondary obligations. Removing it may save far more than the component itself costs. The same principle applies to organizations. A weekly report requires someone to collect data, someone to format it, several people to read it, and meetings to discuss it. If no decision changes because of the report, making it shorter is not the best solution. The best solution is to stop producing it. Deletion is psychologically difficult because addition feels safer. A new feature can be celebrated. A new procedure looks responsible. A new team appears productive. Removing something creates fear. What if it was important? What if a failure occurs afterward? Who will be blamed? Organizations, therefore, accumulate complexity in the same way houses accumulate forgotten objects. Each item once had a reason. Very few people are rewarded for taking it away. Musk has said that if a team never has to add something back, it probably did not delete enough. The exact rule should not be applied mechanically, especially in safety-critical systems, but the idea is useful. Deletion should be a genuine test, not a ceremonial review in which everything survives. Only after deletion comes simplification and optimization. This order prevents teams from polishing things that should not exist. Suppose a production line has 10 stations. Engineers spend months improving the speed of Station 7. Later, someone discovers that changes to the product allow stations 6, 7, and 8 to disappear. The optimization was not merely wasted. It delayed the more valuable redesign. Once unnecessary elements are removed, optimization becomes powerful. Engineers can reduce mass, improve thermal performance, increase manufacturing yield, shorten travel distance, redesign software, improve tooling, or combine components. Tesla has repeatedly emphasized the factory as the machine that builds the machine. This phrase reflects an important shift. A product is not fully designed when the prototype works. It is fully designed only when it can be produced reliably, safely, at the required quality, volume, and cost. A beautiful prototype may depend on highly skilled technicians performing delicate work by hand. That can be acceptable when producing 10 units. It becomes a disaster when producing hundreds of thousands. Manufacturing is therefore not the final stage after design. Manufacturing changes the design. If two parts require difficult alignment, perhaps they should become one part. If a cable is repeatedly damaged during assembly, perhaps its route is wrong. If a robot cannot reach a fastener, perhaps the product was not designed for the robot. If tolerances stack in unpredictable ways, perhaps the architecture needs fewer interfaces. This is where Musk's approach becomes less about personal creativity and more about systems engineering. The object and the process that creates the object must evolve together. Tesla's use of large cast structural components illustrates the principle. Traditional automobile bodies can contain many stamped pieces that must be joined with welds, adhesives, fixtures, inspections, and robots. Replacing a collection of pieces with a much larger casting can reduce part count and assembly steps. The trade-offs are real. Large castings require specialized machines, careful alloy development, quality control, expensive tooling, and new repair strategies. A manufacturing innovation can move complexity rather than eliminate it. But that is exactly the point of first principles analysis. Do not ask whether the new method looks simpler from one angle. Ask whether the entire system becomes better. After simplification comes acceleration. Acceleration means reducing the time between an idea and reliable information about that idea. A team designs something. It builds a version. It tests the version. It studies the result. Then it changes the design. The shorter this loop becomes, the more learning cycles fit inside a year. Consider two teams developing the same machine. Team A performs one major test every 6 months. Team B performs one meaningful test every 2 weeks. Team A may begin with a better design, but Team B receives 12 times as many opportunities to discover mistakes, compare alternatives, and improve. Speed becomes a learning advantage. This is one of the defining features of SpaceX. Rather than trying to make every early prototype appear finished, the company has often built hardware that exists primarily to answer questions. Some tests succeed, some vehicles explode. The public sees dramatic failure, but the engineering value depends on whether the test produces information that changes the next design. A failed test is useful only if it is controlled enough to teach something. Random destruction is not iteration. An experiment needs a question. Which valve failed? Did the structure survive the expected load? How did the thermal protection behave? Was the guidance system stable? Did the engines restart correctly? SpaceX has publicly described flight data and lessons as central outputs of Starship testing. The hardware is not only a vehicle, it is an instrument for learning how the next vehicle should be built. This approach differs from development cultures where failure is hidden because a failed test threatens careers or contracts. If every prototype must look successful, teams delay testing until they believe everything is perfect. That reduces visible failure, but increases the amount of time between assumptions and evidence. The problem is that hidden assumptions do not become true while the team waits. Rapid iteration brings them into contact with reality sooner. But speed has limits. A software update can often be reversed. A rocket failure can destroy hardware. A medical device, public road vehicle, or system carrying humans requires stronger safeguards than an isolated prototype. The correct speed depends on the consequence of failure. Move quickly where failure is contained and informative. Move carefully where failure can injure people, damage public trust, or create irreversible harm. The principle is not to test recklessly. It is to design tests that produce information as quickly as safety allows. The fifth step is automation. Automation can create extraordinary consistency and scale. A machine can repeat a well-designed task thousands of times. Software can monitor, route, compare, and control processes faster than people. But automation freezes assumptions into equipment and code. If the task changes, the automated system may become expensive baggage. Tesla learned this during the difficult increase in Model 3 production. Musk had expected extremely high automation. Some processes proved more complicated than anticipated, and human workers were reintroduced in places where automation had become a bottleneck. Musk later acknowledged that excessive automation had been a mistake. This is a valuable detail because it shows first principles thinking correcting the person most associated with it. The principle was not, robots are always better. The principle became, automate a stable, necessary, simplified process. Humans are flexible. Machines are consistent. Early in development, flexibility may be more valuable. Later, when the design and process are understood, consistency can dominate. The correct sequence is, therefore, not anti-automation. It is automation at the right time. Another important part of Musk's problem-solving style is the search for the bottleneck. A system's total output is often limited by one constrained stage. Imagine a factory with 5 machines. 4 can produce 100 units per hour. 1 can produce only 30. Improving the fast machines to produce 120 changes almost nothing. The system still produces around 30 completed units per hour because everything waits for the slow stage. The bottleneck determines the flow. Musk has a reputation for going directly to production lines, launch sites, or engineering teams when output is blocked. The objective is to find the constraint that prevents the whole system from moving. This can create intense pressure, but the logic is sound. Do not distribute attention equally across every problem. Find the problem controlling all the others. A bottleneck can be a machine. It can also be a decision, a supplier, a software test, a permit, a missing engineer, a poorly defined requirement, a communication delay. Once identified, the organization can concentrate resources until the constraint changes. Then a new bottleneck appears. This approach resembles the theory of constraints. Improving a non-constrained part of a system may create local efficiency without increasing total output. The lesson applies beyond factories. A creator may spend hours improving thumbnails when the real bottleneck is that videos are not being finished. A student may buy new study tools when the bottleneck is sleep. A small company may increase advertising when the real problem is that customers leave after 1 month. Solving the most visible problem is not the same as solving the limiting problem. Mission is another central feature of Musk's method. He usually begins with an extremely large objective: accelerate sustainable energy, make life multiplanetary, reduce the cost of access to space, build transportation systems with radically higher capacity. A large mission does 2 things. First, it provides a filter. A team can ask whether a decision moves the mission forward. Second, it changes the acceptable solution space. If the goal is to improve a rocket by 5%, engineers search for modest improvements. If the goal is to reduce launch cost by an order of magnitude, the existing architecture may no longer be enough. A very ambitious target can force structural innovation because incremental change cannot reach it. But extreme goals also create danger. A target can inspire a team, or it can become a fantasy used to justify impossible deadlines. Musk is famous for aggressive schedules that are frequently missed. Supporters argue that unrealistic deadlines still move organizations faster than comfortable ones. Critics argue that repeated overpromising damages credibility, encourages burnout, and can distort decisions. Both can be true. Time pressure reduces perfectionism and reveals which tasks matter. Too much pressure causes shortcuts, poor communication, stress, and preventable mistakes. The useful principle is not to choose a date that everyone knows is fictional. It is to distinguish physical duration from institutional duration. Some tasks genuinely require time. Concrete must cure, batteries must complete durability cycles, regulators need evidence, humans need sleep. Other delays exist because decisions wait in queues, departments communicate through documents, meetings are scheduled weeks apart, and no one owns the next step. A first principles schedule asks which time is physically necessary and which time is organizational friction. Removing friction can feel like impossible speed. Ignoring physical necessity creates failure. There is also a tendency to confuse Musk's public persona with the work of his companies. Reusable rockets, electric vehicles, battery systems, launch operations, and factories are not produced by one mind. They require thousands of engineers, technicians, operators, designers, suppliers, regulators, customers, and partners. SpaceX also built on decades of aerospace knowledge and benefited from contracts and cooperation with NASA and other institutions. Tesla benefited from advances in lithium-ion batteries, power electronics, computing, manufacturing, and public policy. Recognizing these foundations does not remove Musk's contribution. It makes the explanation more accurate. His distinctive role has often been choosing unusually ambitious objectives, concentrating capital and talent, challenging cost assumptions, accepting technical risk, and creating organizations willing to iterate rapidly. The achievement belongs to systems and teams. The strategic pressure often begins with the leader. This distinction protects us from the great man myth, the belief that history is created entirely by exceptional individuals. Exceptional individuals matter. So do institutions, technologies, timing, public investment, and collective expertise. A useful method should remain useful even after the mythology is removed. So how can an ordinary person apply this style of problem-solving without building rockets or working through the night in a factory? Begin by writing the problem in terms of an outcome. Not, I need a better productivity app. Write, I need to complete 2 hours of focused work before noon. The app is a proposed solution. The focused work is the outcome. This prevents the tool from replacing the goal. Next, list what you know. You have 4 available hours. You need access to certain files. You become distracted when notifications appear. A meeting interrupts the middle of the morning. Then list what you assume. You assume the meeting cannot move. You assume every message requires an immediate answer. You assume you need a new app. You assume focused work must happen at your desk. The facts and assumptions may look similar until they are separated. Now question each requirement. Who created it? What purpose does it serve? What evidence supports it? What happens if it disappears? Do not remove safety, ethics, or obligations simply because they are inconvenient. The goal is not to escape responsibility. The goal is to remove inherited friction. Then delete before adding. Cancel the unnecessary notification before buying a concentration device. Remove one approval before creating a new dashboard. Eliminate one product feature before hiring another engineer to maintain it. Stop one unhelpful commitment before searching for a more advanced calendar. After deletion, simplify what remains. Reduce the number of steps. Put connected tools together. Clarify the decision owner. Use one metric that reflects the outcome instead of 10 metrics that create noise. Then shorten the feedback loop. Do not spend 6 months building the complete product if a 1-week prototype can answer the most dangerous question. Do not write an entire course before teaching one lesson to a real student. Do not invest heavily in a business before discovering whether one customer will pay. The objective of an early test is not to prove that you are right. It is to discover how you are wrong while the cost is still small. Then automate the stable repetition. Once a task is necessary, understood, and repeated often, software or machinery can create leverage. Automation before understanding multiplies confusion. Automation after understanding multiplies value. Finally, identify the bottleneck. Ask, if I improve only one part of this system, which improvement increases the final result? That question prevents busy work. It also creates discomfort because the real bottleneck is often something we avoid. A difficult conversation, a missing skill, a product customers do not want, a leader who cannot delegate, a decision no one wants to own. First principles thinking is not emotionally neutral. Sometimes the most important assumption is connected to identity. A founder believes the original product must survive because it represents years of work. A professional believes a task must remain complicated because complexity proves expertise. A company believes it must stay in a market because leaving looks weak. A person believes they need more discipline when the actual problem is that the goal has no meaning to them. Breaking a problem into facts can expose stories we were using to protect ourselves. This is why the method demands humility. It is easy to challenge other people's assumptions. It is much harder to challenge the assumptions that make us feel intelligent, valuable, or safe. Musk's successes demonstrate the power of refusing to accept inherited limits. His failures and controversies demonstrate that confidence in first principles does not guarantee wisdom. A physical system may be simplified aggressively. A human system contains dignity, trust, law, culture, and consequences that are difficult to reduce to engineering variables. People are not components. A workplace cannot be optimized only for output without affecting health, retention, creativity, and family life. A public platform cannot be managed exactly like a rocket engine because speech, politics, and social behavior do not have stable equations. An engineering method becomes dangerous when it assumes that everything important can be measured easily. The correct lesson is, therefore, not to imitate Musk's personality. It is to borrow the parts of the method that survive critical examination. Start from the real outcome. Separate facts from conventions. Question requirements without dismissing expertise. Delete before optimizing. Design the product and the production system together. Find the bottleneck. Shorten safe feedback loops. Automate only after understanding. Use large goals to reveal structural possibilities. And remain willing to update when evidence contradicts the model. The last principle may be the most important. First principles reasoning begins with what you believe is fundamentally true, but no human being sees every fundamental truth. Your model will always be incomplete. The strongest problem solver is not the person who never changes direction. It is the person who can change direction without protecting their ego. A rocket that explodes does not care how confident the designer was. A production line does not care how impressive the presentation looked. A customer does not care how many hours the team worked. Reality gives feedback without respect for status. Musk's approach is powerful because, at its best, it tries to reach that feedback quickly. Build the test. Measure the result. Remove what failed. Try again. The process looks different from ordinary problem solving because it does not begin by asking what the world usually accepts. It begins by asking what the world actually permits. Then it asks a second question: how much of the remaining difficulty is real and how much was inherited? That question helped turn reusable rockets from an industry aspiration into operational hardware. It helped place manufacturing at the center of electric vehicle strategy. It helped teams challenge costs that had been treated as permanent. It has also produced missed deadlines, failed prototypes, excessive automation, exhausted teams, and decisions that critics argue moved faster than good judgment. The method is neither genius nor madness by itself. It is an amplifier. Combined with evidence, expertise, ethical limits, and a strong team, it can reveal possibilities hidden beneath convention. Combined with overconfidence, it can accelerate directly toward the wrong answer. Elon Musk solves problems differently because he often refuses to accept the problem in the form it was given to him. He takes it apart. He questions the requirements. He removes pieces. He searches for the physical and economic constraint. He builds something that can fail, and he uses the failure to change the next version. The final lesson is not that every problem needs a revolutionary solution. Most bridges should still be built with enormous respect for the bridges that came before them. The lesson is to know the difference between a limit and a habit. A limit is imposed by reality. A habit is imposed by repetition. The difficult part is that both arrive wearing the same clothes. They both sound like this is simply how things are done. First principles thinking asks us to look underneath. Sometimes we discover that the old method exists for an excellent reason. Sometimes we discover that no one remembers the reason. And sometimes, behind an expensive, complicated, impossible problem, we find a collection of smaller truths waiting to be rearranged.